We said that there were two effects in NMR that made it useful for chemists. One was the chemical shift, which we talked about earlier. Here we're going to talk about another effect in NMR called spin-spin coupling that gives rise to information that's useful for chemists. The key point in here, as we said, is nuclei can sense the spins of other nuclei. This is very similar to when we talked about electron spin resonance. Electrons, unpaired electrons in a molecule, can visit other nuclei and sense their spin. Well, here we're talking not about the electron spin, but the nuclear spin. And the nuclear spin can sense the spins of other nuclei. In general, there's two ways one can do that. One is you go through the chemical bonds. So a nucleus will somehow communicate with another nucleus through chemical bonds and sense the spin. And that gives rise, as we will see, to splitting of energy levels. There's another way that one nuclear spin can sense the nuclear spin of another, and that is not through bonds, but through space. And that can be used to obtain 3D structural information, similar to X-ray crystallography. So let's talk about NMR spin-spin coupling. So let's consider a molecule that just has one proton, say chloroform, and we'll look at the magnetic resonance of this. The other three places on the carbon and chloroform are occupied by chlorine. And what we're looking for is the spin-spin coupling, whether this nuclear spin, this is I equal 1/2, with two values of m sub I is equal to plus or minus 1/2, whether this nuclear spin can sense the nuclear spin of, say, carbon, and this is a through bond coupling. Well, let's just look at carbon. Here, this is hydrogen, H1, we know about that, spin 1/2. Here's carbon. Carbon has two naturally occurring isotopes. This is from the webelements.com page. The carbon-12, the one that occurs in most abundance, has a nuclear spin of 0. So that means that this proton won't couple with this carbon-12 nucleus because it has a nuclear spin of 0. There's nothing to couple with. However, there's a 1% abundant carbon-13 isotope which has a nuclear spin of 1/2. So let's synthesize carbon-13 chloride, or carbon-13 chloroform, and look at the coupling of the spin 1/2 here with the nuclear spin of carbon, which is, we just saw, was 1/2, which it itself has two values of m sub I, plus and minus 1/2. And so I don't have to keep writing m sub I equal plus or minus 1/2 and so on. Let's adopt this nomenclature. Alpha will correspond to m sub I equal plus 1/2, or you can also correspond that, say, with an up arrow, electron spin pointing up. And similarly, beta will correspond to m sub I equal minus 1/2, and that will correspond, for example, to spin down. So we're going to use alpha and beta. As we said, the two spin states characterized by m sub I equal plus and minus 1/2 will have degenerate energy levels in the absence of magnetic field. When we turn on the magnetic field, what happens is that these energy levels split, and we can observe a transition between the two energy levels. This is an alpha spin, and this is a beta spin. So we saw for a proton that the m sub I equal minus 1/2 has the higher energy. Okay, now what we're going to do is turn on spin-spin coupling, and what's going to happen? Well, the nucleus, the proton here, will sense two different values of m sub I of the carbon-13, alpha and beta. And those two different values will split each energy level of the alpha and beta spin of the H nucleus, and these then will be the alpha, alpha, and this will be the beta, beta. And now let's make a column here for the protons, and here the column for 13C nucleus. Well, let's see. The nuclear spins will be similar to the electron spins. The lower energy will be where the nuclear spins are paired, have opposite spins. So this would be the lowest energy, alpha beta, where the spin of the carbon-13 is opposite the spin here. And this will be the next higher level, alpha alpha. this will be beta alpha spin paired. That'll be the lower one, and then the higher one will be beta beta. And so now we have several transitions to look at. We ask, well, what are the selection rules? Remember, if the selection rule for here was that delta m sub I is equal to plus or minus 1. How about this, where we have two spins? Well, let's develop another selection rule. Say delta m sub I, where m sub I is the little m sub I for the proton plus the little m sub I for the carbon-13. And we'll say that has to be plus or minus 1 for a transition to occur. So let's look at these various possibilities here. So we want here, this is a beta. Let me just make that beta. I scribbled that. This is beta. And we want a transition between the spin states of the proton. So we're going from alpha to beta. What that means is that we can have a transition from alpha alpha to beta alpha. So this is allowed. Why is that? So we have an alpha alpha goes to an, what did we say that was? An beta alpha. So the nuclear spin here, this is m sub I equal plus 1/2 and m sub I equal plus 1/2. So the big m sub I here is equal to plus 1/2 plus 1/2 is 1. And then here we have a minus 1/2 and a plus 1/2. So the big m sub I here is 0. So this satisfies the selection rule, plus or minus 1, changed by minus 1. And let's see if we can see another transition. It looks like if we go here, alpha beta to beta alpha. So let's look at alpha beta to beta beta. The total m sub I here, we have plus 1/2 and minus 1/2, so that is 0. Here we have minus 1/2 and minus 1/2. The total there is minus 1. So yes, this is delta m sub I here. Looks like it changed by minus 1. That satisfies the selection rule. So that transition is allowed. And let's look at, say, an alpha beta to beta alpha. Alpha beta to beta alpha. Is this transition allowed? I'll put a dotted line here because we're going to find out it's not allowed. Question mark. Well, let's see. Let's go to an alpha beta, and now we're going to a beta alpha. The m sub I here is 0. Plus 1/2 and minus 1/2 is 0. Same way here, m sub I. This is delta m sub I equals 0. That means not allowed. And similarly, so that's not allowed. And similarly, the alpha alpha to beta beta. Let's take a look at that one. Alpha alpha to beta beta. Here the total spin, or total m sub I, is plus 1. And this goes to minus 1. So delta m sub I here is equal to 2. Actually, it's equal to minus 2, final minus initial. So this implies that this transition, alpha alpha to beta beta, is not allowed. So after all that, we find there are just two allowed transitions. And if we look at, here is the transition here. Let's call this occurring at a frequency omega 0. That one of these is shifted to a lower energy, and the other allowed transition is shifted to a higher energy. And it's central symmetric, meaning that this shifts up just as much as this shifts down. So what one ends up with is a spectrum that is split into a doublet. So here is no coupling. This occurs at omega 0, no coupling. With the spin-spin coupling, here is that original, but it's now split down, lower energy and higher energy by the same amount. So now we have a doublet. So it went from a singlet to a doublet. This splitting in energy is given the symbol J. It's called the spin-spin coupling constant. And if you go back here, we see that the difference between this line and this line is 1, 2, 3, 4. 4 times this splitting here. This splitting is the same as this splitting. So this means that this splitting here is, now let me try to write that clearly here. This splitting here is equal to j over 4. This splitting here is equal to j over 2. And the difference between this line and this line is equal to j. So that's just nomenclature. But the big point is that you now, with spin-spin coupling, you have a doublet. And this is for the proton. Let's look at the 13C. Well, if we go back, what you can do is, instead of looking at the effect of carbon-13 on H, you can look at the effect of H on the carbon-13 spectrum, and it's exactly the same thing. You just switch the notation. I is equal to 1/2. You split it, and you split it again, and you get the same pattern. So, for the C13 spectrum, with no coupling, we'll see a single peak. And now, when we couple with the H, we'll see the same thing, the same kind of splitting that we saw for the proton. And this is called J. The two coupling constants, the coupling of C with H and of H with C, are equal because they're symmetric. They go back and forth. So this coupling and that coupling are equal. Now, instead of considering the case where you have different kinds of nuclei, here you have a hydrogen and here you have a carbon, and we're coupling the hydrogen to carbon. This is called heteronuclear coupling. Heteronuclear coupling. Let's do homonuclear coupling, where we're looking at a coupling of H with H. Let's draw a molecule that might occur. Here's a hydrogen, and let's put a chlorine here and a chlorine here. And let's put a bromine here and a bromine here and a bromine here, and I guess I just have one, so let me put an H there. Hydrogen. Now these two hydrogens are in magnetically different environments, so that what one has is this has a different local magnetic field than this, and therefore when one does the NMR spectrum, one gets two lines corresponding to, let's call this A, and let's call this B. And this would be this frequency spectrum. This probably will correspond to, I don't know, A. Let's call it A. And this will call this B. Now, let's couple the nuclei. We'll couple HA and HB. Well, HA will split the nuclear spin of B into a doublet, and B will split the nuclear spin of A into a doublet. So what one gets for homonuclear spin-spin coupling is two doublets. Well, actually, let me be a little more specific here. Put a dotted line there, and we'll put a dotted line there. And again, this is frequency, intensity going up there. We'll call this omega A. We'll call this omega B. So if this, let's be consistent with our notation. Omega B and omega A. This then will be omega B, and this will be omega A. So each peak corresponding to this, each proton here is split. We have a coupling constant here, J, and we'll call this JAB. And here we have J, coupling constant JBA, and JAB is equal to JBA, just like we had for the proton C13 coupling. So this is an example of homonuclear coupling. Now let's get a little more complicated. So let's take the molecule that on this side will have two hydrogens and a chlorine here, and on this side we'll just have a single hydrogen, and we want to ask the question, what effect do these two hydrogens have on this resonance or the NMR spectrum of just this hydrogen? Well, we'll do the same kind of thing we did before. Let's start out, let's label this hydrogen A. We'll start out with those energy levels equal in the absence of a magnetic field, the energy levels corresponding to the alpha and beta spins, the m sub I equal plus 1/2 and minus 1/2. When we turn on a magnetic field, we'll get a splitting, where for the proton, the beta spin will be in the higher energy and the alpha spin will be in the lower energy. So now let's turn on the spin-spin coupling between A and B. So we'll get a splitting this way and a splitting this way, just like we had before. And similarly here for the lower level. And now this level will be beta spin for proton A and beta spin for proton B. This will be a beta alpha, which is a lower energy when you have them opposite spins. Here we'll have the alpha and the beta, alpha and alpha, that'll be higher energy, and then here we have the alpha beta. So that's splitting with proton B. Now let's go ahead and split with proton C. Now before we do this, we should realize that, for example, this CH2Cl group can rotate rapidly around this bond as long as this is at, say, a temperature not so it doesn't make it a solid, so you have rapid rotation and tumbling around in the magnetic field and so on. What that does is make the magnetic environment of B equivalent to the magnetic environment of C. So one says that HC and HB are magnetically equivalent. So what that means when you now turn on the splitting is that you have a splitting like this, but the splitting with C, now this is splitting with C, is exactly the same as you had for B because they're magnetically equivalent. So that means as much as this goes down, this will go down. So this now will have two energy levels here, and this will be split down here. And the same way here, unfortunately, this should be the same as before. So we got something like this. This will be two energy levels here because as this one splits down, this one splits up exactly the same amount. And a split down to give here. So let's label these. This will be beta, beta, beta for proton A, B, and C. This will be beta, beta alpha and beta alpha beta. So you split here, you go down, so that gives you the alpha, and you go up, that gives you the beta. And similarly here, this will be beta alpha, alpha. Same way here, this will be the alpha, 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 all in the same direction, will be the highest energy. Here will be the alpha, alpha, beta, and alpha, beta, alpha, those two energy levels there. And here, this will be the alpha, beta, beta. So those are the energy levels labeled according to that when you have the splitting for B and C. The key point here is that since B and C are magnetically equivalent because of the rapid tumbling around of this molecule, that the splitting that you got originally here, you get a splitting, which gives you two degenerate energy levels here. Now let's look at allowed transitions here. So what we said before was that for allowed transition, we calculated big M sub I. In this case, that's 3 protons, so we have to sum M sub I for A plus M sub I for proton B plus M sub I for proton C, and that has to be plus or minus 1. That's a selection rule. But in addition, additional selection rule when you have more than 2 protons that are coupled is that only one nucleus, or only one, in this case proton, can change sign. What does that mean? Well, you can only have one that goes from an alpha to a beta. So since we're going from alpha to beta in our proton, we're looking at proton A, we can only go from an alpha beta beta to a beta beta beta. So this is one allowed transition here. So the total M sub I here, let's just write down what M sub I is here. This is minus 3/2, 1/2 for each one of those. And here M sub I is minus 1/2. So big M sub I changes by 1, and only one of the spins flips. Here is alpha to beta. That flips. Beta, 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 beta. That's fine. Here's another one. We'll go from here to here. Okay, that's a transition allowed because here we have alpha beta to alpha beta. Here we have beta alpha to beta alpha. This is another allowed transition there. And our final transition will be the alpha 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 to beta alpha alpha. Here only one flipped spin. Here this is 3/2. Total m sub I is -1 half plus 1. This is 1/2. That's okay. The m sub I here, this is -1/2. The m sub I down here is +1/2. So this is a change of 1. This is a change of 1. Those are the three transitions that we expect to observe. Note that this was a transition originally before the spin-spin coupling. That transition is the same as these. So one expects a triplet. Originally you had a singlet. Now this is going to be split by these two to give a triplet. One of the energy levels will be the same. Just go across here. That didn't change at all. One of the energy levels, or one of the peaks, will be in the same place as the unsplit. Then there'll be one at higher energy and one at lower energy. So the spectrum will look like this is without spin-spin coupling. And this is the spectrum of HA. With spin-spin coupling, we're now going to have a triplet. And I'll draw it this way for reasons which will become apparent in a minute, where this is omega 0 right here. So you get a peak where we got it before, plus two satellite peaks. Now the intensity of these will be a 1 to 2 to 1. And one way to look at that is we have two energy levels here, so we got twice the intensity as we had there or there. Okay, so that's splitting of HA. Now let's look at the signal from HB and HC. Since HB and HC are magnetically equivalent, they'll occur at the same place. So if we look at a spectrum just of that without spin-spin coupling, what we will find is a single peak corresponding to HA and HB. The intensity of this peak will be twice that because this arises from two protons. Now when you turn on spin-spin coupling, what will happen? Well, this is a single spin 1/2 nucleus, which is going to split this into a doublet and split this into a doublet. But since they're both occurring at the same resonance frequency and they're magnetically equivalent, what we're going to do is just get a doublet. It really represents separate transitions between HA and HB, but since they are magnetically equivalent, we'll get a doublet. And if this is omega 0, the center frequency here, which doesn't appear, is at omega 0. One shifts lower energy, one shifts higher energy. And as we talked about in class, the relative intensities here for a doublet is 1, 2, 1. For a triplet, 1, 2, 1. For a quartet, it'd be 1, 3, 3, 1, and so on. These numbers generated by the binomial coefficients or Pascal's triangle. What we've talked about so far is coupling between nuclei, C13 and H, for example, or for two protons whose separation on a frequency scale is large. So, for example, this is 13C and this is a proton here, very large separation because they have larger gyromagnetic ratios. Or in the example we used before, this was, say, proton A, and this was proton B, and this frequency separation was large. So one can couple with methods we saw before. In NMR terminology, this is called a AX system, where A is one nucleus, X is the other, and they're separated by a large amount on the frequency scale. Now what happens if these two resonances, let's look at homonuclear splitting, these two resonances become closer and closer together? Well, let's look at the case where we have just two protons and they each, say, HA and HB, and they each interact. So if we now turn on the coupling, spin-spin coupling, what this will do would be give a doublet, two sets of doublets. This would be HA, which is split by that proton. This is HB, which is split by that proton. Now, as the resonance frequencies, so this will be omega A, and this will be omega B, as the resonance frequencies start to become closer together, what one has is still a doublet, but the intensities of the doublet are no longer equal. The ones on the side here go lower. So these two are for HA, and these two are for HB. You see a pattern like this, you say, oh, it's a 1-3-3-1 splitting by triplets, a quartet here. But in fact, no. What happens when you have this is called strong coupling, is that the intensity of the peak vary. And if you have very strong coupling, what's going to happen is you have a single peak here. So these collapse into a singlet peak. The intensity in these outside lines decreases and decreases as these two lines become closer together. And then with very strong coupling, you got a single peak. So we're not going to talk about that, but what that means is that energy levels now are becoming closer together. And as the energy levels come closer together, they start to mix, just like we saw in quantum mechanics. If we have two degenerate energy levels, we can then mix them to form two other energy levels, like bonding and anti-bonding orbitals, for example. Well, the same thing here. You're mixing two wave functions, and you change the shape until you eventually get a single line for very strong coupling. That's when they're totally degenerate energy levels. So we're not going to talk about this, but just to be aware of it, and you probably talk qualitatively about what happens when you have strong coupling, where the separation in energy between the two energy levels is very similar, or becomes close to the J coupling, the coupling between the separation between the two lines in the doublet. So you probably talked about that before in organic chemistry laboratory and so on, so you should be aware of that. Secondly, let me make another point. Remember when we said that if we have these two energy levels and one goes to a higher energy level and one goes to a lower energy level, when we turn on a magnetic field, and we label this one as m sub I equal minus 1/2, and this is m sub I equal plus 1/2. So if we look at if we call this the final state, and this the initial state, and we're going from the initial to final, so this corresponds to an absorption. We said that delta E was equal to the nuclear G factor times the Bohr nuclear magneton times the magnetic field times m sub I. So that is the splitting here. That's what that is. The total splitting will be the final state, which is G sub n, beta sub n, B times minus 1/2, minus the initial state, G n beta, oh sorry, I guess I keep writing beta, but I guess we're using mu for the symbol for the Bohr, or the nuclear magneton, so we'll put a mu there, be consistent with our previous notation, mu b, mu n for nuclear, all right, there we go, b, times plus 1/2. This comes out to be negative Gn mu n b. So for this scheme, we have a negative. Delta E is negative, which implies since E equals h bar omega, omega is negative. All right, so some textbooks you'll have a not minus sign there. However, remember that omega was gamma, that's the gyromagnetic ratio, times the magnetic field B. And we also found that the gyromagnetic ratio can be negative. So if that is negative, then the frequency is negative and this becomes positive. And whether you put m sub I equal minus 1/2 plus 1/2 or m sub I equal plus 1/2 and minus 1/2 depends on the nucleus you're looking at, whether the gyromagnetic ratio is positive or negative, which, as we said earlier, really means whether the nuclear magnetic moment is positive or negative. So some nuclei can have a negative magnetic moment leading to a negative gyromagnetic ratio.